Okay, let's get started with this week's workshop that is on BERT. So BERT was actually developed by Google. So if you like, you can see that there are a lot of references that I have put on for this particular demo. So this demo is actually like referred from the a very good blog instead. So if you are like getting started to BERT model, or even conceptually, if you are getting started to the like concept of transfer learning and all, you can like visit this blog. And if you want to like have a deeper understanding of like how the BERT model works, or the behind the scenes of the BERT model and all, then there's a sequence of blogs or papers that you can read. So actually, it all started from the NLP community was like highly gifted from the discovery of LSTM and RNN networks. So LSTM's GRU, they were quite useful in sequence modeling. So NLP tasks like carried a lot of these networks were from LSTMs and GRUs. But there was one breakthrough from a paper known as Attention is All You Need. So that was the beginning of the attention mechanism. And from there on, we got transformer model. So the transformer was like you can say like basically LSTMs and RNNs on steroids. So it's like a much enhanced version of LSTM, where it is much more useful for like if you're trying to encode some long sequences, or for language translation, or for a chatbot, for instance. So in these cases, you have to handle long conversations. So transformers were especially very much useful in these tasks. And from transformers, then there were different large scale models that were developed. OpenAI developed GPT-2, and then Google brought BERT. So BERT, I guess, was before GPT, if I'm not wrong. So these are some of the models that use transformers attention mechanisms, and you can go through these references all in one to like get a deeper understanding of all these network architectures and how they actually work behind the scenes. Over here, in this particular demo, I'll just like get walk you through a simple use case of text classification, like a sentiment analysis using BERT model. So I'll first like just get you introduced to the use case, and then we will walk along, and somewhere if some details are needed, I'll just let you know. And I'll also point you to appropriate references where you can get more details about those particular models. So yeah, starting off. So um, I will be using PyTorch's BERT implementation in this case. If you want, you can use Keras as well. The reason I'm going with PyTorch is because of the easier implementation. If you look at Keras, then or TensorFlow has a sub package called TensorFlow Hub, and from there you can access the BERT model. But for that you will have to do layer subclassing. So subclass a layer, build your own BERT maybe class layer, and then do so. That involves a bit of complexity. So I just went through this workshop for PyTorch. It's quite easy one, so it's not that you will have to know some nitty and gritty details of PyTorch. Okay, so getting you introduced with the actual use case. So this is basically we are working on the essence of this use case is sentiment classification, and here we will be doing a movie review classification. So there is a corpus, a data set consisting of movie reviews, and you will have to predict whether it's a positive review or a negative review. And obviously, the reviews will be in text, so there is no numeric review like a rating. That makes it quite easy. So since we are dealing with NLP, it will be a text review. So in this, for example, you can see the review, the input is a text, say a visually stunning rumination on love, and you have to predict whether it's a positive review or a negative review, and it correctly classifies this as a positive review. So for this particular code, we are using DistilBert. So there's no as such a big difference between BERT model and distilled BERT model. You can say that distilled BERT model is actually it's a smaller version of BERT, and this PyTorch BERT model is being open sourced by a team known as Hugging Face. So it's a lighter and faster version of BERT, but rest of the things are almost the same. And since this is just for demo purposes, obviously I will be using distilled BERT. It's much faster and easier to train, like not much heavy on the GPU resources. So this is how we will build the framework. So there's an input data set. We will pass it through the BERT model, which will do the embedding and like vector space representation of the text data. I'll get in more detail when we progress in the workshop. And the output of the BERT will be the input to our logistic regression model. And you can guess why we are using a logistic regression model, because um, you can think of it as that way because it's, after all, eventually a binary classification task that we are handling. So the final output will be a vector of probabilities referring to 0 or a 1. So hence the last, you can think of it as that way, that the last layer of this neural network architecture would be a sigmoid function, or we can use a logistic regression model. So for this case, we are just importing scikit-learn's logistic regression model. You can do it either way. Like if you're using an end-to-end TensorFlow implementation, just add a dense layer with a sigmoid activation function. But in this case, we are just adding up a layer of logistic regression imported from scikit-learn. So I'll just quickly move on to the code. So first I install transformers. This is a library from PyTorch. Okay, so I do the import. This cell handles all the importing. The line next to the import torch is import transformers. So this is PyTorch transformer module. And this is the data set that I have read. And here you can view uh, the first 5 rows of how the data set actually looks. So you can see that it's quite a simple, clean data set that we can use for prototyping. So the first column named over here has 0 is the actual text review, and the label that has been denoted as column name 1 is the actual label. So 1 over here represents a positive review. Let me check that whether 1 is a positive review. Yeah. So 1 represents a positive review and 0 is a negative review. So this is a classification data set that we'll be using, and this is the shape that I have printed. Now for faster training and all, I'm just using the first 2000 samples of the entire data set. So I have named that as batch_1, and this is what we will be using for the rest of the demo. And just we did a like class uh, uh, distribution count maybe, so you can see that out of the 2k entries, there are 1000 ones and around 960 zeros. So these, both the classes are quite balanced. If you see, just a statistic that we have done this, no particular use for this later on. Okay, now over here we are loading the BERT model. So the first line, you can see that we are loading the distilled BERT model. So this is the model class, the tokenizer class, and the pre-trained weights, which constitutes the entire model. And you will also see that we have also imported tokenizer. So what BERT does is, if you read the paper, BERT has its own tokenizing mechanism as well. So it's every package, for example, NLTK, Spaceseed, have its own tokenization implementation, and so does BERT. So BERT doesn't handle tokenization in a very trivial way. So you will see later on that even some words get tokenized. So that's why it's much more useful that if you are using BERT as a model, it's much recommended that you use the BERT's tokenizer class. And the last 2 lines, you can see that I have defined a tokenizer variable, and I have defined the model variable that is imported from the model class. So this is the entire model that will get downloaded when you are trying to implement your own code. So this is actually the concept of transfer learning, that we are downloading an already trained model, and we will just do a feed forward procedure of using those models weights in our demo. So I have shown you a similar kind of thing in Spacey as well, where we had downloaded the Spacey model, which was used for like the embedding of text to vectors. So this is similar to this. This is known as transfer learning, which you guys are already familiar with. Next, we will prepare the data set so that we can make it in accordance with how the input should be given to the BERT model. So first, we will apply tokenization. So we will tokenize the text that is each and every row of the data set. So over here, you can see that batch one, and we have indexed on 0 because we are just taking the first column, and the first column were the reviews. So we are doing reviews, and we have applied the dot apply and then the lambda function of tokenizer dot encode. So what it does is that it will take each and every row of the data frame for that first column, that is the movie reviews, and then it will tokenize it. So this is a very beautiful visual representation of the process that I have just described in the code from the blog post. So for example, if it's the first row of the data frame, the text is a visually stunning rumination on love, and you see how it tokenizes the BERT tokenization, and you see that uh, it does like it has its own algorithm for tokenizing. And then after breaking it in separate words, and even some words like getting breaking into two different parts into tokens, BERT introduces two more special tokens. The first token that you can see is CLS, and the last token SCP. So SCP stands for separator, and CLS stands for classification. I'll get into more detail of especially the first token CLS in the later course. And in the last stage, you can see that is the third point. They substitute the words with their token IDs. So every token has its token ID in the BERT database, and it gets replaced with that. Even the CLS and the SAP special tokens get replaced. So to generate CLS and SAP, we have used this argument of add special tokens equals to true. So separator, as the name suggests, is used for separating two sentences, and CLS will be used for classification, which we are actually going to do in this demo. So moving on. Mm, so yeah, first of all, I'll just make you visualize the tokenized variable. So since we just fetched the first column, you can see that all rows of the data frame for the first column have been tokenized and replaced with the token IDs. Now, since I will be creating an array of this, you might realize that the sentences length will be different, and so will be the length of the token array. So therefore, we will have to unify all the lengths. So for that, I have done a padding exercise. So this first block of for loop is nothing but I'm just calculating the maximum length of the entire all amongst all the rows. I'm calculating which row has the maximum input length sequence. So I'm just storing that in a variable called max underscore length. And then with that help of that variable, I have padded all the arrays with zeros. So if you finally look at the padded array variable, you see that it's same as the previous tokenized variable, but just to unify the length of all the entries, we have padded with zeros and then converted it into a NumPy array. So now you can also look at its shape, and it's 2000 because we had chosen 2000 entries, and the 59 dimension each. So yes, this is almost in the ready format. And then moving on, we will also this is an important part which you can which you should take care of. So since we have added some extra info on the token IDs, that is zeros, that is just meant for padding. So we must explicitly tell BERT that this padding is not to get confused with, and you can just ignore these zeros. So this can be done by a method known as masking, where we'll mask the padding. So how this is done? I just define a variable and attention underscore mask, and I'm doing np.where padded not equal to 0, just make it 1, or if it is equal to 0, make it 0. So you will see that the attention mask is of the same shape as that of the padded variable, and that makes sense. So where exactly and how will you use this attention mask variable? I'll just let you know in due course. So moving on, I'll just get you introduced with the structure, how we will be giving the input to the BERT model. And this is how we will be doing. We have already downloaded the pre-trained distilled BERT. So you can have a look at the visualization as well. So you can see in this next cell, I have just like converted the padded array into a tensor object. So this is just like a NumPy array encapsulated into a torch tensor object. And and similarly, I have done the same thing for attention mask. And then I'm doing the like feeding this into the pre-trained model. So I have defined a variable last hidden states, and that is equal to model. And over here, I have given the input IDs, which is this entire corpus of sentences over here that we have defined, the padded one. So yeah, so this is the first argument, and the second argument is the attention mask that we had defined. So the attention just let the BERT model know that we have to ignore the zeros, and that is just for padding purposes. So that shouldn't be given importance. So now comes the important part where you need to see the format of how the BERT gives the output. So just look at this part carefully. So first, showing the code before like actually showing you anything, I'll just show you this visualization. So if you see the left hand side of the visualization, this is the output of the variable of the model, which has been named as last then states variable. So you see there are 2000 rows where each row corresponds to one sentence, and it's a total of three, like there are three tensors. So it's a three-dimensional tensor. And there is 768 number of hidden units and 66 positions, tokens in each sequence. Now, since we are dealing with classification, remember I showed you the token of CLS. So, what exactly CLS is, that is a different thing. But CLS is a token that we will use for classification, and we are only interested in this particular token. So you can intuitively think of CLS as maybe some mathematical aggregation of rest of the tokens. So it contains the info of the entire sentence for that particular row, and that is just the CLS token that we can fetch out. So how we will do that? Over here in this figure, in the second part, you can see that the last hidden state, and why it has done 0, you can just ignore it as of now because it returns a tuple. So we are just accessing the array. So that's why. And the main part that we will, the first colon represents that we will be taking all the sentences, that is all the 2000 rows, and then we will just take the CLS position. So hence we are doing 0. If we would have put colon over here as well instead of 0, then it would take the tokens for the trained tokens and the vectors for each of the word. But CLS you can think of as like it considers the info of all of the words of the sentence, and hence we will just be using that token, and hence we have given 0. And each vector representation of a word is a 768 dimensional vector. Hence, we have to obviously take all the dimensions of that vector, and that's why the last colon represents all the hidden layer outputs. So you can guess what the weight would be after doing this. So yes, the weight before doing this step was 2000 cross 59 cross 768, and we did this process, we get 2000 cross 768 because we ignore the like all other words and just are interested in the CLS token tag. So what we have in hand is the vector representing the CLS token. And the CLS token, you can think of it as like has the information for the entire sentence. So this is the output of the BERT that we are actually interested in, which has the shape of 2000 cross 768. Now we can fetch the labels. So we had defined batch one, and we take the first column of the second column of that, which consisted of the label information. So from now here onwards, the things get pretty straightforward. So now since we have our input data in shape and everything, we just go with a fixed pipeline. So first we do the train test split. We are doing the train test split on features. That is the final output of the BERT model over here, which has shape 2000 cross 768, and the labels. Labels is all the label information. So have a look over here. This is how the final um, model looks like, data set looks like. We do the uh, train test division over it. And obviously this is a simplified pictorial representation because train test like randomly samples the data set as well. So it's not in order, but yeah, you guys have already gone through these steps in your assignments as well. So once this is generated, we will just fit a logistic regression model. So this chunk of code over here is just a grid search for finding the optimal parameters. So especially the C parameter in logistic regression, that which handles the regularization strength. You can search for a bit of values. So over here, I have just simply trained it on logistic regression model. So I've imported logistic regression from scikit-learn, and I fitted on the X and Y values, where X is the train features, that is the entire matrix of shape 2000 cross 768, and the output of the labels, which is a 2000 vector representing ones and zeros. So we train on this, and once we train, then we get the output, and you can see the accuracy on the test features, that we get a 0.838 accuracy, that is around 84% accuracy, which is a pretty decent accuracy for like this exercise. Obviously you can increase this accuracy with finer tuning of the model, especially the BERT model. So you see the essence over here is actually the BERT model that we have used. Now if I give you a bigger picture of what exactly we have done over here, we have used two components. One was the actual classification part that we are interested in, and for that we have used logistic regression. But before applying logistic regression, we have to convert our input, that is text, into numeric values, since these algorithms only understands numerical values. So for that, that if you apply the knowledge what you have studied till now, there are some other options that you could have done. For example, you could have done TF-IDF, or if you go for more sophisticated mod transfer learning approaches, you could have done word to vec. So you could have installed or downloaded a word to vec model, and then the word to vec would have generated vector representations of the sentences corpus. But in this case, instead of word to vec or glove, we decided to go with a more sophisticated model, and we chose BERT. So BERT in this case, for this particular use case, we just used for like uh, transforming the sentences into a different latent dimension space, that is same motive what we had from word to word, even though the working of BERT is entirely different. So that is a different thing. But yes, so this is what we had used for. But this is one of the downstream tasks that we had used, have used BERT for. But obviously, there are much more tasks where BERT can be more useful. For example, the natural language translation part, creating a chatbot. So for those, it's much more useful because their word to vec and other these techniques won't prove to be that much useful. So yes, this was the main um, motive behind using BERT for this particular demo. Obviously, you can read more about these models in the references that I have provided. You can go through the actual paper of BERT, transformers, attention mechanism, to get a higher understanding of how these exactly work and where do these exact like come into play. So these are some interesting things that are going into NLP community, and you can definitely have a look over these.